Hello everyone. So welcome to this new session. So in our last classes we have discussed all the homogeneous and non-homogeneous types of equations along with the different kinds of problems of different values of r of x. Along with that also we have discussed one more topic, that is Cauchy's homogeneous linear differential equations. So in today's class we are going to deal with the last topic of this module. The name of the topic is Legendre's homogeneous linear differential equation. See the word? It is Legendre, okay, not legendary. Yeah, Legendre's homogeneous linear differential equations. So here it is similar to Cauchy's. So in place of substitutions we have a few changes here. Okay, the rule remains the same, that is the r of x should be replaced by where the value of x should be replaced in the terms of z. Okay, that is r of z. Okay, and here in the differential equation, this differential equation is of the form, in Cauchy's equation how we had x power n, right? Also x power n minus 1, like that we were having. So here in place of x we have a plus bx. Okay, everywhere a plus bx, a plus bx. Yeah. The Legendre's equations would be of this form, where the a0, a1 up to a power n minus 1 an are constants. So this equation is called the Legendre's differential equation. So here we need to substitute. In place of Cauchy's we had substitute z is equal to log x, right? So here we need to substitute the value of z equal to log of a plus bx, okay, where a plus bx corresponds to this term which is given, okay, in the bracket. Okay, also we can write e power z is equal to a plus bx. Okay, so in case of Cauchy's we had been doing e power z equal to x, right? Yeah, so here in the Legendre's equation we need to substitute e power z as a plus bx. Also we can substitute a plus bx into dy by dx as small letter b, which corresponds to this term, into dy. So in Cauchy's, in place of a plus bx we had x, right? And here in place of a plus bx we had x. Wherever a plus bx is there, in Cauchy's we had it as x. So here the same thing, in place of x write it as a plus bx, and for a plus bx into dy by dx we need to substitute as b dy, and a plus bx the whole square d square y by dx square is equal to, again this, see, here it is b, right? So when the power increases, the power of b also increases, that is we need to write b square d into d minus 1 y. The same thing goes for the cube term, b cube d into d minus 1 into the extra term d minus 2 into y, and so on. By substituting all of these values in the given Legendre's equation, we will be reduced with the linear differential equation with some of the constant coefficients. Yeah, so this was all about the topic of Legendre's differential equations. So now we will solve few problems. After that we will be very clear about this topic. Okay, yeah, so now we will start with the problems. So this is your first question of this topic, that is 1 plus x the whole square d square y by dx square plus 1 plus x into dy by dx plus y is equal to sine 2 log of 1 plus x. Okay, here the same thing, we need to do a few substitutions. So this is of the form a plus bx, right, where the value of a corresponds to 1 and plus bx. So here the coefficient of x is 1. Okay, so the values for a and b are, so here in the given question a is equal to 1, also b is equal to 1, right? So now we need to substitute a few of the values, that is here we need to substitute a plus bx is equal to e power z, right, where e power z corresponds to the value of a is 1 and b is 1, so 1 plus x. Okay, also we need to substitute z is equal to log of a plus bx, so 1 plus x. Okay, so if we substitute log of 1 plus x as z in place of r of x, so here in case of r of z we get it as sine 2z, right? R of z would be equal to sine 2z if we substitute z is equal to log 1 plus x. Yeah, so now again we need to put few more substitutions, that is 1 plus x the whole square d square y by dx square is equal to b square. The formula is b square d minus 1 y, right? So in place of b, the value of b here is 1, right? So 1 square is 1 d minus 1 y. Also 1 plus x dy by dx is equal to, again the value of b is 1, so 1 into dy. Yeah, so now using these substitutions we are going to put them in this equation. Okay, yeah, so now after all the substitutions we get 1 plus x whole square d square y by dx square can be written as d into d minus 1 into y plus dy, right, plus y is equal to sine 2z, right? So now multiply this d square minus d, here there is plus d plus 1 into y is equal to sine 2z. So minus d plus d goes, so the remaining terms are d square plus 1 into y is equal to sine 2z. Okay, so here again we need to put the same thing. To find the complementary function, we need to put d is equal to m according to the auxiliary function. So this would be m square plus 1 is equal to 0. So again now we can solve this directly, since we don't have an m term. Bring this 1 to other side, m square equal to minus 1, m equal to minus plus or minus square root of minus 1, m equal to plus or minus square root of I square. So we get m equal to plus or minus I as our roots. So our complementary function is c1 cos, the value of beta is 1, so c1 cos z, the function is in terms of z, right? c2 sin z into e power alpha, here is 0, right? So I am not writing it again. E to the power 0 is 1, right? So I have not written that. So this is our required complementary function. Okay, so now we need to find the particular integral. Yp equal to 1 by f of d into r of z, right? 1 by the value of f of d is d square plus 1, r of z is sine 2z. So here we need to replace, since this is of the second type, d square by minus of a square, where the value of a here is 2, so we get minus of 2 square equal to minus 4. So yp we get it as sine 2z divided by minus 4 plus 1. So our final answer we get for particular integral as minus of sine 2z by 3. So minus 4 plus 1 is minus 3, right? So I have written that minus in the numerator. So this is your particular integral. So now we'll write the y. So now we can write y equal to yc plus the y2, right? So y is the complementary function, we got it as c1 cos z plus c2 sin z minus the particular integral is sin 2z by 3, right? So now in this we need to replace a few terms as we did in Cauchy's. So here we need to replace z is equal to not log x, this time we need to replace z is equal to log of 1 plus x. Okay, also in place of e power z, so here in this term there are no e power z terms, right? Yeah, so we need to replace only z by log of 1 plus x. Okay, so our final general solution would be looking like c1 cos of log 1 plus x plus c2 sin of log of 1 plus x minus sin 2 log of 1 plus x divided by 3. So this is your required final general solution. Okay, where we have replaced the value of wherever there are z terms, we have replaced it by log of 1 plus x. Okay. Yeah, so now we'll get to the next question. So this is your next question. So the question given is 2x plus 3 the whole square d square y by dx square minus 2x plus 3 into dy by dx minus 12y is equal to 6x. So here in this r of x term we have only 6x, okay, but here we need to replace r of x by r of z, right? For that we need to replace the value of x since we have only an x term. So whatever we should do after the substitutions, we need to do the substitutions in such a way that at the end we need to find the value of x here, okay. Yeah, so now I'll show that how we should be doing it. So the first thing is the value of, let's write the values of a and b. So this is of the form again a plus bx, but the terms are written in a reverse manner. That is, the first a term is written in the second place and the bx term is written in the first place. So here we can compare and say that this is a and this is b, right? So our a is equal to 3 and b is equal to 2, right? Yeah, so now we can write e power z is equal to a plus bx, right? That is 3 plus 2x. Also we can write z is equal to log of a plus bx, so again 3 plus 2x. Also in the r of z term we needed to find the value of x, right? So in these two cases, which is the easier equation that we can find the value of x? So here we have log, right? So in this becomes tougher to find the value of x. We can find it, but this is a bit long method. So in this equation, by simplifying this equation, we can find the value of x, right? That is, if we bring this 2x term to one side, so this would be e power z and this 3 will become minus 3. So we can write x is equal to e power z minus 3 by 2. So now from this equation we have found the value of x, right? So now our r of z term would be looking like, we had 6x, right? So it would be, now here by simplifying this we got the value of x, right? 6 e power z minus 3 by 2, okay? So that is 6 e power z by 2 minus 6 3s are, right? So this would be 18 by 2, right? So again 2 1s are 2 3s are, 2 1s are 2 9s are. So we get 3 e power z minus 9 as our r of z term by simplifying it, right? Yeah, so here we need to substitute that only. So now again we have few more substitutions left, that is we need to put 3 plus 2x the whole square, right? Or 2x plus 3, that's one and the same. D square y by dx square as b square d minus 1 y, where the value of b here is 2, right? So 2 square is 4 d minus 1 into y. Also 3 plus 2x dy by dx can be written as, the value of b is 2, right? So 2 dy, okay. Yeah, so now let's put this in the equations. So now the first term is 2x plus 3 whole square d square y by dx square, that is directly write it as 4d d minus 1 into y, right? Minus of 2x plus 3 dy by dx, that is 2 dy minus 12y is equal to the solved the r of z term, that is 3 e power z minus 9, right? Yeah, so now we need to solve this. Multiply 4d to the term 4d square minus 4d, so here minus 2d is there, minus 12, y is equal to 3 e power z minus 9, right? So here we can solve this, that is 4d square minus 4d minus 2d is minus 6d minus 12 into y is equal to 3 e power z minus 9. See, we have reduced this equation in this form. So now again the procedure remains the same. We need to put d is equal to m according to AE, and we get 4m square minus 6m minus 12 is equal to 0. So now we need to apply the quadratic formula. So let's apply the formula quadratic. In the place of b we have minus 6, So it would be minus of minus plus 6. Square root of minus 6 the whole square is 36. And since we have minus 12, so this becomes plus 4 into 12 into 4. So 12 fours are 48. So 4 into 12 into 16 into 12 we get it, right? 16 12 are how much? 32, 16, 192 divided by 4. 2 into 4 is 8. 2a, right, in the denominator. Square root of 192 plus 36. 202, 212, 222 and 228 divided by 8. Yeah, so now by further solving this 6 plus or minus, so here we can split this square root of 228, right? So if we split it in two table, we cannot, so we can write this as 4 into whatever is the answer for 228 by 4. So while solving that I got it as 57. Okay, we can split and write this 228 as 4 into 57 by 8. So 6 plus or minus square root of 4 is 2 root 57 by 8. So m equal to, so here we can take 2 a common in the numerator. It would be 3 plus or minus square root of 57 divided by 8. So 2 ones are 2 fours are, so our root we get it as m equal to 3 plus or minus square root of 57 by 8. Okay, so this is our required root. So the total roots are 3 plus root 57 by 8 and 3 minus root 57 by 8. Okay, so if you see, observe carefully, this is not of the form alpha plus or minus I beta. Okay, this is not, and there is no imaginary term here. So we need to be very careful by solving this. Some of them will be in excitement of solving that there is an imaginary term, and they will directly write the imaginary term complementary function. We need to write it that c1 cos beta x, c2 sin beta x. So no, here there is no imaginary term. So this is our two roots where these two roots are different. So our complementary function would be looking like c1 e to the power, first root is 3 plus root 57 by 4. Okay, this is 4, right? So 2 ones are 2, 2s are x plus c2 into 3 minus root 57 by 4 into x. Okay, yeah, so this is our final complementary function. So since again I am repeating it, this is not an imaginary term, since there is no any imaginary term here, so we cannot write in the form of alpha plus or minus I beta. Yeah, so now we are going to solve for particular interval. So it is 1 by f of d value is 4d square minus 6d minus 12 into r of x is 3 e power z minus 9. So again we have two terms for r of z. So again we need to solve it, once for 3 e power z and once for y. For that we need to solve for yp1 and yp2 again. So our yp1 could be given as 3 e power z 4d square minus 6d minus 12. So here since we have minus, so our yp would be looking like yp1 minus yp2. Okay, since here we have minus. So now let's solve for yp1. So here the value of a is 1, so 3 e power z divided by 4 into 1 square minus 6 into 1 minus 12. So you know, right, how I have substituted the value of d as 1, since we have solved so many problems. Okay, I'll write it again. We need to replace d by a, and the value of a here is 1, right? This is of the form e to the power ax, first type, right? Yeah. So our yp1 would be looking like 3 e power z divided by 4 ones are 4 minus 6 minus 12. That is 4 minus 6 is minus 2, minus 2 minus 12 is minus 14. So yp1 is minus 3 e power z divided by 14. So this is our yp1. So similarly, let's try to find the yp2. So yp2 is equal to 9 divided by 4d square minus 6b minus 12, where the value of d we need to replace it by 0, right? So since we can write it as 9e power 0x, so 9 divided by 4 into 0 square minus 6 into 0 minus 12. So therefore our yp2 we get it as minus 9 by 12, right? Only this term left, these two terms will go. So we can reduce it by 3 3s are 3 4s are, so our final yp2 we get it as minus 3 by 4. Okay, yeah. So now we have written that yp is equal to yp1 minus yp2, right? So yp would be equal to, yp1 is minus 3e power z by 14 minus of minus 3 by 4, right? So yp is, if I write the first positive term, 3 by 4 minus 3e power z by 14. Okay, so if you want you can solve this further, okay, by taking the LCM. That is 14 3s are 42 minus 4 3s are 12 e power z divided by 14 4s are 56. Okay, you can solve this like this also. So this is your required particular integral. So now finally we can write y is equal to yc plus yp. We have yc we got it as c1 e to the power 3 plus root 57 by 4x plus c2 into e to the power 3 minus root 57 by 4 into x plus yp we got it as 42 minus 12 e power z by 56. So this is your y term. So this is not done yet, so now we need to replace a few terms, right? That is, we need to replace e power z by log of, we need to replace e power z by 3 plus 2x, right? And we need to replace z by log of 3 plus 2x. So here this is z, okay? This is z, okay? I have made a mistake here. Since the function is in the z form, right, parameter, okay? Sure, this is z, okay? Yeah, so now let's replace the terms. So what we get? c1 e to the power 3 plus root 57 by 4 into z is replaced by log of 3 plus 2x, right? Plus c2 into e to the power 3 minus root 57 by 4 into again log of 3 plus 2x plus, I'll write it down here, 42 minus 12 into e power z is equal to 3 plus 2x, right, divided by 56. Okay, yeah, so we can solve this. So since there is log and this is again of the form b log a, so we know that this is b log a is equal to, I'll write it here, b log a is equal to log a power b, right? So yeah, we'll write that. So let's see what we get. c1 into e to the power log of, where a is 3 plus 2x to the power of 3 plus or minus, so 3 plus root 57 by 4, right, plus c2 e to the power log of 3 plus 2x to the power 3 minus root 57 by 4, right? Right, plus 42, multiply this 12 inside, so we get 12 3s are 36, and minus 12 into 2 is minus 24x divided by 56. Okay, yeah, so here e and log gets cancelled, so the remaining terms are 3 plus 2x into 3 plus root 57 by 4, right, plus c1 is there, okay, c2 into 3 plus 2x, 3 minus root 57 by 4, and plus 42 minus 36 is 6, right, 6 minus 24x divided by 56. So this is your required general solution. Okay, so we need to be very careful by solving these kind of problems. Okay, all the terms are very important. So this you have made a mistake here, said that I have written x, right? So you should not be doing that, since the parameter here is, we know that r of x should be replaced by r of z. So the parameter x should be replaced by z. So whenever you write the particular integral and the complementary function, we should write that in terms of z. Okay, we should not write that in terms of x, because at the last step we are going to replace the values of e power z and z. Okay, yeah, so this is your final answer. So that's all for this session. In the next session we are going to solve a few more problems of this, and we are going to wind up this module. Okay, thank you.